All right, good morning. How's everyone doing? So welcome to the 14th annual Rutgers Energy Institute annual symposium. I'm Frank Felder with the Rutgers Energy Institute, or REI. As probably everyone here knows, our mission is to integrate Rutgers expertise in the physical sciences, social sciences, policy, engineering to address the major energy challenges. Obviously, greenhouse gases, climate change is a huge one, but certainly not the only one. I'll be brief because you're here not to listen to me, but from our great set of speakers. But I do have some preliminaries. First of all, I'd like to thank the REI, the Rutgers Energy Institute, supporting schools. The School of Arts and Sciences, Dean Peter March, the School of Environmental Biological Sciences, Dean Bob Goodman, the Business School, Dean Lei Lei, the Engineering School, Dean Tom Farris, who you'll be hearing from in a moment, and from the Blaustein School of Planning and Public Policy, which is where I am housed, Dean Vanu Thakkaria. Just as a point of personal privilege, Vanu joined Blaustein in October. She's in the back. Her background, one of her many areas of expertise is transportation and its intersection with big data, and obviously that has a large overlap with energy, so welcome to Rutgers. I do want to thank the prior director and administrator, Professor Paul Fikowski and Beatrice Beer, for all their efforts. We wouldn't be here today but for Paul and Bee's efforts since the founding of REI many years ago. I also like to thank Preeti Thankaraya, who's my assistant. She's over there. She has a good sense of not to listen to me. So whenever I make a suggestion, she politely looks at me and then does the exact opposite, and that usually works out. And usually, I mean all the time. I won't recognize all the dignitaries here except for Governor Jim Florio. There he is, he's always up front. As I say, it's always a good day when you see Governor Florio, so thank you very much. It is possible to be politically successful and a decent human being. Who knew? Yeah. Let me give you a quick review of the agenda, and then I'll turn it over. I'll introduce our two first speakers. I'm going to introduce, and we're going to introduce speakers in pairs. We're going to keep the biography short, again, so to maximize their time and participation by the audience. After each major speakers, the four major speakers, will have time for one or two questions, but then we'll have, at the end of the morning, the late morning, a 45-minute panel where all the speakers will come, and we'll move immediately to audience participation. We also have three terrific workshops after lunch, starting at 1 p.m. They're on the second floor, which you can access by going up these stairs or through the lobby. And if you take a look at the agenda, even if you haven't registered, feel free to attend one of those three workshops. And then for the hardcore, we'll reconvene at 2:30 just for a brief debrief, informal debrief, see where we are and how we can move forward. So with that, let me briefly introduce in tandem the Vice Chancellors for Research and Innovation, Prabhas Moghe and Tom Farris. Let me start with, I'll do both and then we can applaud. Prabhas Moghe was appointed to the inaugural Vice Chair of Research and Innovation in January of 2018. He's a distinguished professor of biomedical engineering and joined Rutgers engineering faculty in 1995, and he's a pleasure to work with. Tom Farris was appointed Dean of the School of Engineering in July of 2009, is also on the faculty of Mechanical and Aerospace Engineering. Prior to joining Rutgers, he spent 23 years on the faculty of Purdue University, so he knows what a Hoosier is, and if you know what a Hoosier is, please let me know. Please join me in welcoming Vice Chancellor Moghe and Dean Farris, and we'll have them come up one at a time. Great, thank you.
Welcome. It's very good to have you here, and on behalf of the 5,000 students and the 300 faculty and staff of the School of Engineering, welcome to our new home, Richard Weeks Hall of Engineering. We had the dedication of this building on November 15th, so in a week's time it will be 6 months old. Those of you that were here for November 15th will remember this. Those of you that weren't here on November 15th, it snowed like crazy that afternoon. That's why you didn't come, right? That's why you didn't come. And for my Asian colleagues that follow the lunar calendar, water is life, And so there's no better indicator of success than having snow the day of a celebration. That followed the groundbreaking. Some of you may remember the groundbreaking in the tent over by the Biomedical Engineering Building, and we had all of Tony Calcado's staff holding the standards of the tent because it was so windy and rainy that day. So lots of good omens for Richard Weeks Hall of Engineering. It's Richard Weeks without an initial. There are 5 Richard Weeks. This month, actually, May of 2019, is the 100th anniversary of the founding of the Weeks Stevedoring Company by the grandfather of our 1950 graduate, Richard N. Weeks. Okay. Richard N. Weeks is the namesake of the building. He graduated in 1950, so it's not nice to talk about people's ages, but I'll let you do the arithmetic, all right? He's still incredibly sharp, takes it all in. We had a very nice civil and environmental engineering symposium in this room on Friday about the built environment, about infrastructure, and I don't do red and blue, but about this idea that this country really has to get its act together and do things with infrastructure. We had the Commissioner of Transportation from the state here, Ms. Gutierrez Cassetti, and trust me, Richard N. Weeks takes it all in. There's an organization in the city for big construction and tunnels and so on. It's an organization sort of on the construction side, like on the academic side, the National Academies. It's an honorific. They also do philanthropic things. Mr. Weeks has now been a mole for 50 years. Richard X.S. Weeks, next in generation, like so many of our Rutgers engineers, they come to Rutgers, they have great success after studying Rutgers engineering, but they send their children off to private schools, right? So Richard S. Weeks went to Hopkins, also went to the Kennedy School, so he knows a lot about public policy. They're really in the middle of policy and actually the actual construction of offshore wind. A little more involved in the activities off of Cape Cod than they are in the activities off of New Jersey, but actually very fitting nicely in with the theme of this conference. So that's Richard N. Weeks, Richard S. Weeks. Richard M. Weeks, Matt, is getting a PhD at Rutgers in food science in the laboratory of Professor Chakindas. The building itself is very cool. It's actually a living laboratory. The atrium is actually a working atrium, chilled beams for the HVAC, windows that can open depending on what the environment is outside. Laboratories for energy, including a terrace with possibilities of putting in wind turbines and so on, and studying the performance of the wind turbines. In the classroom across the hall, in the longest beam in the building, it's actually instrumented with strain gauges, so we can see the performance of the building in practice. So, new home for the School of Engineering. Very pleased to have you here, and the theme of today is very important to our school. Thanks very much.
Good morning, everyone. Good morning. Come on, we can do better.
Good morning.
So firstly, kudos to Tom for, isn't this a magnificent building? And you should see how this building comes alive with students from all walks of the campus converge here. This is sort of the happenings place. This is like the yard meets academics on this campus. All right, so I've been in this role for over a year now, and I am dreaming big. And what I'm looking for are partners. So I have the academic deans, who are fantastic as a group. And as you know, the Rutgers Energy Institute, after 14 years of great oversight and governance by Paul Felkowski, the question for REI was, where does it go from here? We've switched our budget models at the university. An institute like the REI is really a massive network across the institution. How do you support this? So I took this on as one of my first test cases. And I'm proud to say that we have Frank Felder in this position. We have Dunbar Birnie. We have a great group of people. And you'll probably meet them today. But the REI is in very good hands. And the plan is for the REI to get even stronger as we move forward. That's one of my big priorities. The second thing I'm trying to do here is to cause more intellectual collisions on the campus. I mean, Rutgers is a great research powerhouse, but sometimes people don't know about this. And so we've got to get this message out to our citizens of New Jersey, to the students of New Jersey, to bring out-of-state students and global citizens to the university. So we have been engaged in ideation forums on the campus. And I think many years from now, when people remember me, they probably remember the word ideation. I'm proud to say that many of those ideation projects that were featured, the last one in November was held here, the one prior to that was in the core building, were on photocatalysis, imaging for energy. We've had people like Chuck Dismukes, Shishir Chandawat, Sang-Yuk Lee, Rick Ryman, all of these people, scientists, entrepreneurs, engineers, have featured at those forums. I had this chat with ExxonMobil a few months ago, and the question was, can we partner with a company like Exxon to develop sort of a think tank? And the challenge that he threw at me, the gauntlet, was interesting. You know what he said? He said, we're not interested in the horses. We're interested in the jockeys. And what that meant to me is that we have to grow the inventors, the entrepreneurs who think, conceive, create, develop, discover, and nurture these ideas. And the people that make this possible on a campus are the students. So we're trying to create constellations of these students, these postdocs, around these intellectual jockeys. And imagine what happens when an intellectual jockey meets another intellectual jockey. To make those collisions essentially amplify everything for us. And that's how you grow these initiatives and then these centers. So I am very excited about today. I'm also very excited that we've decided to feature and focus on one signature initiative today, which is the Offshore Wind initiative. It would be amazing for us to have this initiative lead to Rutgers being in one of the lead institutions, among many others, but also New Jersey, not to concede this one. Not to concede this one on so many levels. So I think the presence of Orsted here is very promising. The presence of a governor is very, I think it's a great sign for us. A big round of applause for the leadership in the room. And I believe that many of the roads for our success will run through a word called collaboration. And so we've got to get our people together, collaborate at every level. Don't think about who takes credit for it. Collaborate, and great things will happen. Thank you, Frank.
Okay, it's a pleasure to be introducing our first two speakers, and I want to add to the welcome that Prabhas and Tom have given. This wind theme is a great one to feature and is very interdisciplinary, and there are many different areas at Rutgers where we provide expertise that are valuable for this. And so you think about wind, you think about variability of power generation, you think about energy storage, the grid, battery technology, new materials for developing wind turbines, and all of these different systems. So network today, I'll be happy to introduce you to people who might fall into some of those categories. So it's my pleasure actually to now introduce our first two speakers. And I'm going to do them in reverse order just because I'm tasked with doing two at a time, and we'll see how that works. So our second speaker will be Annmarie Carlton, who's an associate professor of chemistry at the University of California, Irvine. And I'm really pleased to welcome her back because she received all of her degrees here, and so welcome home. The ultimate goal of her research is to inform policymakers about atmospheric and environmental effects of anthropogenic atmospheric pollutants. And so let's welcome Annmarie. And our first speaker will be Scott Glenn, who's a distinguished professor here in Marine and Coastal Sciences, co-director of the RU Cool Coastal Observatory, Oceanography Leadership, yes. He graduated from MIT and has spent 30 years, more than 30 years, working on ocean science, and we'll tell you more about it. So welcome, Scott.
Okay, thank you for that introduction, to everybody else for coming here. I'm very excited to be speaking about this. As Dunbar said, I've been here for like 30 years now, and I want to talk about the power of partnerships for this. This is exactly what Prabhas was talking about, that power of partnerships that we've been demonstrating here for 30 years. Our topics today are wind energy and the environmental awareness and the shared economic success. I think that was Frank's title. So this is my outline today. I got about 30 minutes. And so I'm going to do an abridged history of ocean observing. It's a discipline that really started here at Rutgers under the leadership of someone called Fred Grassley. We're going to talk about offshore wind in the mid-Atlantic and why it's important for us. I'm going to talk about this proven value of partnerships that we've demonstrated and why this oceanographic advantage that we offer to people here is so important. And then talk about our way forward in the future, which is the New Jersey Wind Institute. This here is one of our gliders. I'll talk a lot about gliders. You saw one as you entered. These, sure.
Speak up a little bit if you could.
Thank you, Mike. How's that? Much better back there? Okay. So this is one of our gliders. That's out. There's our underwater robots. This is the famous one that left Tuckerton, New Jersey about 10 years ago and made it all the way across the Atlantic and then into the Smithsonian, led by students. And so this is where it all started, Tuckerton, New Jersey. 30 years ago, back in 1989, with the vision of Fred Grassley. He was a visionary ocean explorer, used to go down in these submarines, discovered all those vents, the vent communities and chemosynthesis. He's the one that invited me here back in 1989 and brought me down to Tuckerton to show me this field station and talked about this incubator that we wanted to build for ocean observing. And we talked well into the night and we drew pictures on napkins. And when we recovered in the morning and our heads were clear again, we got an artist to start drawing some pictures. And this is what we did, where we had cables going all over the seafloor and robots roaming through the water and ships at sea and all this data coming to shore. And why did we do that? It was to communicate the importance of the ocean to people. If we want to communicate the importance of a forest to people, people have walked in the forest. They understand the forest. You can do that. If you want to communicate the importance of a city to people, people have walked in a city. They understand it. You can communicate that importance. When you try to communicate the importance of the ocean, very few of us have the privilege of working at sea. And that was the piece that we wanted to do. How do we bring the sea to the shore? How do we bring the sea to our classrooms? How do we bring it to our workspaces? And that's what we did. And so with this concept, we moved forward with this idea. I met Fred. I met the leadership. I was inspired by them. I met the students. They are hardworking students. And with all that, I had a lot of choices back in 1989. And in 1990, I chose Rutgers. I chose New Jersey. So Jersey was something I started to do 30 years ago. And after 10 years of innovation and partnerships, we moved from this drawing here on a napkin, I won't say what bar, into something that we had implemented. Fred gave us the job of implementing this. He paired scientists with engineers. So I was paired with an engineer named Chris Van Alt. And when you pair scientists with engineers, innovation happens. And these were the innovations we did. In 1996, we put out the first cabled observatory in the world, something that led to NSF investing $500 million in cabled observatories. In 1997, we built the first REMUS, the autonomous vehicle, and deployed it first in the ocean at Tuckerton. In 1998, we put up the first HF radars, the first CODAR systems on the East Coast that were permanent to map the surface currents for things like the Coast Guard. In 1999, we deployed the first glider in salt water, the one that 10 years later flew across the Atlantic. And so innovation after innovation came to this head in 2001 in something called the Coastal Predictive Skill Experiments at Tuckerton. Hundreds of collaborators from around the world converging on this space to get the most sampled ocean they've ever seen. This led to the Integrated Ocean Observing System 10 years later. And so we look at going from this picture to that picture over 10 years. In the next 10 years, we went to those it's the same drawings, the same artists, I guess, from the West Coast this time. Everything's West Coasty. And the same sensors out there, cables on the seafloor, sensors and gliders and robots going through the ocean. $500 million invested in IUs, $500 million in OOI. But they're very different programs, very different cultures. It's a very T-shaped world out there. IUs is broad across the top, given that us broad spatial context of what's going on in the ocean. NSF is the opposite. The OOI is the base of the T, deep dives, many, many sensors at co-located locations to give us that time series view. So the broad spatial view combined with the deep dive and the time series is what we had. Two very different cultures. Can anybody guess how many institutions or what institutions have leadership roles in both of these programs? What institutions may have leaderships? There's only one. It's a very simple question. Only one institution in the United States of America has leadership roles in both of these programs. Where is that? Rutgers. Correct. This is the place that is a leader in both of these. No other university. If you want to come to leadership roles in these two networks, choose Jersey. And when we got the experts together 10 years ago, ORAP, we assembled the experts in DC. The experts always go to DC. They come up with these big plans, and we made the recommendations for offshore renewable energy in 2011. They said we should use ocean observing through the IUs and OOI networks. That was 10 years ago. All that was developed. So the renewable energies was coming on, on the scene. They said it's offshore, a lot of that. And so we need to know that ocean. And so that's when I met people like Chris Orleth about a decade ago, when these recommendations are coming out and we're trying to move this forward. So why offshore energy in this area? Why offshore wind? If we look at the United States population density, we have a high population density. We have a lot of customers out there. So it's good to have customers for this electricity. If you look at where the money is, the economic input, here it is. It's clustered here. It's the biggest, 1.56 trillion in this area. Economics, the economic output like that, it takes power, right? It takes electricity. So if you look at where the power is needed, there's the intense power demand right there in our mid-Atlantic region. But here's our, 2017, here was our power distribution. A lot of it nuclear, natural gas, very little renewable. The governor has set new goals for renewable energy, up to 50% in the next 10 years. So how are we going to do that? We're going to do that with things like rooftop solars in the cities or in the car parking lots. A huge amount of expertise like that here, right at Rutgers, transforming our campus with that. But we're also going to do it with wind energy. Those are the two pieces. So we have to do that with wind energy, and then that means we have to look at the resource. Where is the resource? And so here's the resource. If you look at where the wind is, it's not onshore, it's offshore. So we have to go to sea. That's important. That's why we need to know this ocean better. That's why we need to involve those IUS and OOI activities. So we're going to sea. We have to get that power that's offshore. We have to bring it to shore, just like we brought those observations to shore. Here's the area that we have to do it. Luckily, we have a very shallow and wide continental shelf. That's a very important asset for us. If the water's deep, you have to have expensive platforms like these out here. But our water is shallow, so this continental shelf, we can put the jackets and the monopoles out there. These type of construction for the offshore wind towers that we have. And these are very tall towers, as you can see here, getting close to the height of the Eiffel Tower. But offshore, because we have that shallow water. However, that shallow water is home to a lot of other activities. We have some of the biggest ports in the US here on the East Coast right here. And if we look at the vessel traffic that comes in and out of here through our Marco portal, this is another Rutgers and Monmouth University activity. I don't know if Rick Lathrop is here. Okay, here's all the ship traffic that goes across this shelf. That's another part of our economic development that we care about. So we have to preserve this. We can't harm that activity. We have to preserve our fishing activity. These are very important fisheries in our area. The scallops is one of the most productive fisheries that we have here. And then the pelagics, the ones that go in the water column in this area. So these jobs are important too. And then we have whale migrations through the area. Other things live out there. Other mammals live out there. The right whale is one of the endangered species that we care about. The calving grounds are here. The feeding grounds are there. So they have to migrate through. And the migration north is usually offshore. And then they feed up here in the summer, and then they come back south in the winter, close to shore. And here's one of the whale listening stations at the entrance to New York Harbor. Equinor, I think, is a partner in this. I think they're here. So, okay, here's a fin whale, lots of fin whales. Here's the right whale. There's that big December pulse. Okay, that's what's expected. Here's a straggler. He's a little late getting up to dinner. But that's what we have to worry about, because there's not many of these right whales out there. There was only 7 born this last breeding season. And that was a lot. So we have to protect those whales. And we have to worry about the birds on the flyways, especially the Atlantic flyway with the water, with the birds there. And that's why New Jersey DEP cares so much about the birds and the bird censuses that they do when we look at offshore wind. But we still must do something. We can't stop, because Bob Kopp will tell us the sea level is rising. We have here the Climate Alliance, another big New Jersey Rutgers initiative where we're looking at sea level rise, and it's inevitable. Here's the 2 different scenarios, high and low carbon. So for the next several years or decades, we're going to have this rise in sea level. This is right here at Atlantic City. And what that does is it changes the baseline. The baseline is relentless. It's moving up for water level. But what is going to really hurt us is the hurricanes. And here's the two hurricanes that came in, Irene in 2011 and Sandy in 2012. Irene was come up at this coast. We knew well in advance when it was coming, but its intensity was over-predicted. It de-intensified as it came across. So big things were expected. Everybody was ordered to evacuate, and nothing happened. The next year, Sandy came along. Everybody was ordered to evacuate. Nobody believed it. And it was worse than expected. So we can do track beautifully. We're lousy at intensity. And that's important because the shelter in place or evacuate decision is based on intensity. And that has to be, and there's a lead time that has to be sent to people. And to do this properly, there's two things we have to do. From the environmental side, we have to improve our intensity forecast, but we also have to get with engineers like Annmarie in the Center for Transportation to say, how do we evacuate those people in time? So we close the gap in these forecasts from both sides. One, how good is the intensity forecast? And two, how fast can we evacuate? A science and engineering problem. So we have to switch to more renewable energy because not switching is going to have dire consequences. And so this is the plan. The states understand this. Here's our plan for all these states in here. The different levels of renewable in New Jersey, 50% over the next decade. That's a big switch from the nuclear and natural gases to this. And if we look at how New Jersey plans to do it, there's these 3 solicitations in place. 2018 is the one that's going on now. And we'll soon have some announcements as to who will be doing that development here in New Jersey to get us there. And if we look through the whole, through all the regions here, this is the federal side, the wind energy leases and the estimates of the commissioning year, all starting in 2020 through 26, all along this coast with all those people here ready to accept that energy. This is where the development is going to go on. A lot of these companies are from Europe. They're coming to our ocean. The ocean's different, but our ocean is very similar to those same markets in Asia. So it's a stepping stone. You come from Europe to the US, learn how to operate, everybody can go to Asia because Asia looks more like us. And so realizing this, we have the Rutgers Energy Institute. And as Prabhas said, it's this new energy institute that we're putting together with Frank. And the first thing we did with Frank is we're going to form this working group. And Bob Kopp was there. Remember? You had the name? All right, Wind Innovation Working Group. We did this 16 units of Rutgers, all collaborating together. This is one of those collisions on campus that we're talking about. Scientists, faculty, engineers, students, all working together in this Wind Energy Institute. And so I'm going to focus not on the whole thing, just one side here, this environmental side, and quickly talk about that. So this is our observatory now. It's on the other campus, the SEBS campus, where we have this is our cool room, our Center for Ocean Observing Leadership, where the students can sit there and experience the ocean every day. That's the most important piece of equipment, that table. That's where they do their organic chemistry homework. And then something happens in the ocean, they pop up and look at it as it's going on. We have satellites that we're collecting data from space. HF radar network, the largest HF radar network in the world. Second largest, Korea. 500 glider deployments, more than any other group in the world, except maybe the Navy, and they won't tell us. The data all goes into ocean models, where it's assimilated. So ocean models, which are then coupled to atmospheric models to give us that ocean influence on the atmosphere. And so here, through this data collection, this control center, all this data comes in. And through NOAA, we've gained the certification. required so that our government is the same quality control as all data from the government. It has that same quality assurance, and then it gets assimilated into our ocean and atmospheric models that we're using to forecast in this area. This is the key piece of the oceanography that we want to bring home today. One concept, the concept of the coal pool, the mid-Atlantic coal pool. In the winter time, this is a cross-shelf section. There's this depth over here and distance offshore, moving along that arrow. And as you go offshore in the wintertime, it's cold at the top, it's cold at the bottom, it's cold everywhere. Okay, what happens in the summer? The sun comes out, it beats down on the surface gets warm. Warm water is light, cold water is heavy, this warm water floats. And there it is. The most intense thermocline on Earth is right here off New Jersey. And here's this coal pool at the bottom. Hey, let's do this movie again. And this is a map of it that we get by assimilating all that data. You can't see this feature from space. It's invisible. The only way to go out and find it is to touch it. Go out and touch it with a person in a boat. Or, as we do, go out and touch it with a robot. Those yellow robots that we have right outside. And we map that coal pool. And that coal pool is important for several things. One of those things is that it controls the circulation on our continental shelf. And one of our biggest customers is the Coast Guard. And we partnered with the Coast Guard because the Coast Guard, on their daily average, is 13 lives saved. Not every life is saved. The challenge is not going to get the person out of the water. We have brave people that can do that. The challenge is finding them. We don't know where they drifted to. We need a better drift model. And by using the radars in our network and the models that we have and these blind tests that we did, they were able to make us operational for search and rescue, the first in the country. And as a result, if you look at the models that we produced, that ocean model in our radar network, we have the most used search and rescue product in the entire country in this region. There is no place safer to operate than the mid-Atlantic because of what we're doing in the ocean. If we look at our fisheries, that same coal pool is affecting our fisheries. Fisheries care about temperature. They're very migratory here. The fish are often near the bottom. The satellite will tell us what's at the top. But if we go with our gliders, we can see where that coal pool is. And then you can build niche models for the different fisheries that we have with the fishing community involved. And we can decide where is it likely to find these fish. And if you know that, you can get the NOAA people that are regulating the fish to go to the right spot. And then everybody wins. The regulators are happy, the fishing community is happy, and the scientists that make that possible, they're here. They're Josh Kohut and John Manderson. The fishing community will say they're the first scientists we've ever trusted. Because they listened, they helped, they used everybody's expertise and they combined it. We all look at, okay, the other part, ocean acidification, the other side of the global warming issue, right? Part of it is that this heating up, the CO2, the greenhouse effect. The other is that the ocean is getting more acid. That affects the shellfish. The new sensors, the ocean acidification sensors, they're being miniaturized. They're being put on the gliders. And so now that a glider is offshore, it can tell us what the acidification, what the pH of that ocean is. And we're getting more pH measurements in like one deployment than in all of history. We're also using it for looking at hurricanes. And we put those gliders out there and we find new ocean processes like this ahead of eye cooling that goes on where this front end of the hurricane is so intense it changes the circulation, it changes the ocean in a matter of hours, something that we were not taught in oceanography school. And that has an impact on the hurricanes. This is so new and fundamental. It's in nature, but it's not in our hurricane forecast models. And so, as a result, we've changed our approach to forecasting hurricanes in the United States. Hurricane hunters. This is what we used to do. It's like a soccer game. Jim, that's your job, right? The hurricane hunters down in Miami. And so we used to dress up in white and chase the hurricane. We chased the ball like in soccer since 1946. But we know to win at soccer, not only you got to dress up in white like this, you also have to dress up in yellow and protect the goal. And so for the first time, we put out the fleet of hurricane gliders and protected our coasts from both chasing the ball and protecting the goal. And here is one day, September 11th, in the life of this hurricane glider fleet with 31 gliders deployed in picket lines as the hurricanes were coming in. So the hurricane hunters are chasing the ball, we're protecting the goal. And here it is, 62 community guiders, 20 times more ocean data than ever before. We choked the data assimilation of the models. We have to improve that. And if those gliders are out there doing this work, here's the acoustic sensors. There's several companies that are putting acoustic sensors out there to track the whales. We can be out there protecting us from hurricanes and tracking the whales at the same time. These are our partners in Texas with a couple of those whale sensors. And so now how does that impact us here for offshore wind? Here's a phenomenon called sea breeze. Everybody that lives at the coast knows sea breeze. The land heats up, the air rises. Here the ocean is cold, the air sinks, and it comes in as a big breeze. On the landward side, here's that front. It starts here and it moves inshore. It sweeps across the state. You can see it on that inshore side because it collects all the bugs and birds and things in that area. And if you see that sea breeze, or you feel that sea breeze come across, it's warm on one side, cold on the other, a huge temperature difference. That's on the inshore side. But remember Fred Grassley. Fred Grassley told us nobody knows what's going on the offshore side because we don't work there, we don't walk there. We walk here. What's going on the offshore side? That's where the wind energy is going to be. That's what we have to learn more about. One of the impacts that we have to learn more about is the effect of the water, the cold water. And here, with the Board of Public Utilities support, we look at this phenomenon called coastal upwelling. That cold pool, that water's below the surface, when the winds are from the south, this is what causes that cold water to come up to the surface right at the beach and spoil your beach day. It also has a big impact on the sea breeze because now you have very cold water right at the surface that's going to intensify the sea breeze. And if you look at why this is important, this is the longest slide of the whole event. Here's the power load from PJM in black with the peak in the summer. Here's the sea breeze impacts. There's a peak in April, in the spring, and a peak in the summer. Blue is the upwelling that occurs when it occurs. So in the summer, when there's a big load on the power grid, we have sea breezes and we have coastal upwelling. And so if we look at how we want to predict that, here is what the ocean looks like in April, right here during this peak. Cold everywhere, warm all on land. That's a very easy sea breeze to model. There's two different temperatures, and that's it. What does it look like in the summer? Right here in the middle of the wind energy area, there's that cold water. It's warm, it's cold, it's warm. Which way does the sea breeze go? We don't live there, we don't know. We have to do that research. And why do we have to care? Why do we have to do that research? Here's the average wind speed by month in that time period. Here is the low in the wind speed. The low in the average wind speed is right when we need the peak. And that's when the sea breezes are impacted by the upwelling the most. So that's where we need to do the research. And so we've done that with the Board of Public Utilities. We set up our atmospheric models here. We've been running these for days and for years in the area, doing that sea breeze research in this area. And here's just one example. Here's that cold upwelling events that is occurring on our coast on some summer day. This is the product that we produce with the New Jersey Board of Public Utilities. And here's the product we produce by some federal agency that should go nameless because they fund all my hurricane research. So I won't put it up there. It doesn't even resolve what we have in New Jersey. And so you look at the wind fields here at the hub heights of those turbines, and you see very different wind fields in these areas as a result of that ocean phenomena impacting the atmosphere. So all these activities that are going on, the different data portals that allow you to access these wind, these years of wind data that we have are all going to be talked about later today in the workshops. You'll see those workshops this afternoon. There'll be 3 people there. Joe Brody, somewhere here. Joe Brody, funded by this New Jersey Board of Public Utilities to be the marine meteorologist to help produce these activities, to help enable the offshore wind industry. Dave Robinson is here somewhere, the New Jersey state climatologist that has records of the weather going way back. And Josh Kohut, you can't see it. Josh Kohut is here. Josh Kohut. All right, so we got a state meteorologist, a state climatologist. Josh Kohut is nominated to be the first state oceanographer in the country. We have to follow through with that. We have to get him appointed. Texas will beat us if we don't do something. I want to have the first state oceanographer in the country. They will be at the workshop to show you how you access this data in the portal. And so, too many. One more slide. Beautiful. There you go, one more slide. There's this innovation, the Wind Energy Innovation Working Group, where we started. And the governor has called for the formation of the New Jersey Wind Institute, the Wind Innovation and New Development Institute. And to get there, Rutgers has teamed Josh Kohut with Kevin Lyons to take this and the partners from 14 other colleges and universities and implement the partnerships and ideas that we have here to form this. And that's our future. And this is why when Prabhas says we hope they choose Jersey, this is why we're building this Wind Energy Institute. This is where the innovation, the 30 years of innovation is going to continue for another 30 years. And that's why I think we should choose Jersey when we think of offshore wind. Thank you.
We have time probably for 2 or 3 questions.
Oh, okay.
So we have time for, let's start with 2 questions.
Oh, I should have taken more time.
Any questions?
Why not reach across the border and partner with some of New York universities?
We are doing exactly that. Those New York University proposals are due, when are they due? In the next, in a week. Yes. We are partnering with many other states across the board. There's a whole regional activity that goes on at many levels. There's the Marco level that has that portal that we talked about. There's the Maracus level, which is the ocean observations and atmospheric observations that Josh is going to show later on. And there's the most immediate one is the NY Certic Hall, where there'll be many of those partnerships. Yes, sir.
Now, how is your work integrated with design wave analysis for the Mid-Atlantic continental shelf?
The design wave analysis is not that integrated with this. Now, the waves are important for the real-time activities. And so the ocean models, of course, are coupled. There's three-way coupling, right? There's the atmospheric model, which drives the waves and drives the currents, and all three of those are coupled because then we look at the sediment transport. Okay, so but the actual design wave part of it, that's probably from years and years of measurements, maybe some modeling.
I'm just wondering how much wind power, how much energy can we get from wind power, as far as percentage for New Jersey?
The goal is 50%. The goal is 50% in the next 10 years. And so that's what we're hoping for.
That's all wind, solar.
Wind and solar, sorry. Yes, Gene.
I actually have two questions. One is your funding, and is it sufficient? And the
Never.
Never is. I know. But can
What
you
type of
actually
question is
accomplish
that?
what you want to do without the money? And the second one, I'll wait on.
No, it's impossible to do it without the funding. You always have to have a government sponsor, a government advocate, a government hero to do this.
BPU, obviously, the federal government,
The federal government.
DOE?
DOE, yes, there is interest in that, but the big federal government funder is NOAA.
Okay.
NOAA cares a lot about the fisheries, things like that. They care a lot about the hurricanes.
Yeah.
And so hurricane funding is very big for us, but it's all related. If you're observing for a hurricane or observing for a whale, it's the same sensors that are out there.
And then, well, my second question is, based on your predictions for 20 years from now, my theory has always been, talking to experts, that the offshore wind can be baseload generation, which would basically replace the nuclear power plants for New Jersey. What do you think?
It has to,
Okay, that's good.
because the nuclear power plants are getting older. One has already been decommissioned, and eventually the others will be. They're still operating now, but eventually they have to be decommissioned. They have a lifetime, and so they have to go. And what do we replace that with? We don't want to replace it with coal. We want to replace it with renewables.
So the intermittency of wind along the coast is an issue. If
Yes.
You're talking a baseload, PGM baseload line going from Virginia up to New York.
Yes.
Would that make the intermittency problem less? Or
It always helps because then you have the intermittency is spread over many different pieces of the mid-Atlantic. And so low wind here will be balanced by high wind there many times. It won't always be balanced, but then there's also the onshore storage piece of it. And also, there's so much load that it's going to all be used no matter how much we produce out there. So we're going to continue to, I hope,
I'll stop
produce
there.
renewables. Okay.
That's all right. Never stop asking questions, but at least for now. Great, thank you very much, Scott.
Thank you.
Thank you so much for having me. Is it on? Can you hear me?
Lift it.
Lift it more.
Closer to your
No. Okay. Is that better? No. Maybe I should just hold it or something? I'll try now. Do you hear me now? Okay, so thank you so much for having me. I really do feel like I'm home. I lived in Crosby. It's one of the buildings right behind me for 3 years. Like Mr. Weeks, I have 2 sons. They both study engineering, and we believe in public school, so they go to public school. So I'm going to talk to you today about collaboration that I did largely with Frank Felder while I was here at Rutgers. When I first interviewed for my faculty position, they asked me if there's anyone I wanted to meet, and the only person I explicitly mentioned was Frank. And they didn't put him on my list of people. And, yeah, so I asked you to get coffee with me on my own time, and we've been chatting ever since, and I've learned a lot from that collaboration. So I'm going to talk about work that we did together, and Mike Moeller and Caroline Farkas were students, and Kirk Baker is a collaborator from the US EPA. I think it's always important to start by putting your work into some context. So here I'm showing you two images of the George Washington Bridge. Maybe you've heard of it. Okay, so in the 1970s, EPA did this really cool thing where they hired artists to document the environment in their communities. And one of my favorite artists from this project is Chester Higgins, because he lived in New Jersey. So he took this picture in 1973, and this was just a regular day. And when I first saw this picture, I was shocked, and I showed it to my mother, and I said, is that really what it looked like? And she was shocked that I was shocked. She said, it always looked like that. All the bridges look like that. And more recently, the air quality in that area is better. There's still some regional haze in the background, and so air quality is not perfect. But one thing I like to tell young people, is my students, this was their grandparents' generation, and they didn't have Google. If they had a calculator, it was probably the kind you had to plug in. And they took us from air that you could literally chew on to this. So there's no excuse for us to not be excellent. Okay, so when we think about air quality in New Jersey, the two pollutants that we typically think about are ozone and fine particles. So ozone makes you sick, particles kill you. And when we think specifically about electricity as part of the energy matrix in New Jersey, power plants emit sulfur dioxide, which forms sulfate particles. Power plants emit NOx, which go on to form ozone and nitrate particles. And these air pollutants are associated with a wide variety of disease, including premature death. Also, it's quite well established in the literature that air pollution reduces crop yields. And towards the end of my talk, I'm going to show you where I think that might be starting to happen in New Jersey and where I would look if I was still here. So the goal of our project has been trying to quantify these negative impacts of energy and electricity choice that are external to the electricity cost. Okay, so when we first met Frank, one of the things that he could do is he can model heat output or heat input of the PJM, that's the Electricity Reliability Network that New Jersey is a part of, because that data is typically proprietary and it's not easy to get access to, but Frank can model it. So what I'm showing here on the x-axis is total PJM power generation, and on the y-axis, these blue dots are keyed to the ozone concentration, and these green dots are keyed to the PM 2.5 or particle concentration. And we can see there's a pretty clear trend, right? There's not a straight line, but as energy production in PJM goes up, air quality decreases. My students are really, really good at social media. Caroline developed a reduced form version of Frank's model, and she would start to predict high electricity demand days ahead of time and get people to send her pictures of peaking units turning on in their communities, and they would send us back pictures like this. Okay. So there's a lot going on in these plots, but let me just walk you through them. In both of these, the blue trace is the PJM power, and then the lines behind that are particle concentration measurements from two different networks. So on the right, we have hourly PM 2.5, and we can see it's not perfect. Sometimes there's some separation, but in general, there's high particle matter concentrations in New Jersey when the PJM power output is high. And then here what I'm showing you is another network measurement that's averaged over a longer time period, but we get chemical speciation for what's actually inside those particles. And almost all sulfate particle mass in New Jersey is derived from power plant emissions. And so this red part of each pie is sulfates. So what I want you to take away from this plot is that when energy production in PJM is high, particle mass concentrations are high, and sulfate is a big component of that. When power output in PJM is low, particle mass concentrations are low, and sulfate is a very small component of that. And there's this very clear link between electricity generation and what we breathe in. So if you could just humor me for a second and take a deep breath. maybe a little deeper. Okay, so you just breathed in billions upon billions of different chemical molecules. Some were present as gases, some were present as particles. You breathe them into the deepest part of your lungs where they're mixing with your blood and literally becoming a part of your body. And the person you love most in the world is not that close to you. Okay, so we wanted to see, now we know electricity is affecting emissions, and then emissions gets us to some air quality scenario. So we coupled a lot of different models, and we learned how to talk to each other. So sometimes people who are interested in economics and people who are interested in science and engineering, maybe can be some conflict of words, and I'll show you a few examples of that. So the first thing that we did is we took Frank's energy model called DASER, and we used that to improve the national emissions inventory, and I'll show you some examples of this in a few minutes. And so interestingly, if you were to talk to people who do air quality research, they would tell you that the electricity sector emissions are the best and most well characterized. And I'm going to show you how that's maybe not saying so much. The model that we used has emissions from a variety of different sources. So we have area sources that would be everything like your dry cleaners or Burger King. If you've ever driven by a Burger King, you see they have big plumes. And then there's biogenic sources. So these are plants and trees. If you've ever smelled a Christmas tree or cleaned with pine sol, those organic gases go on to react, and we account for that chemistry. We have emissions from mobile sources, and then we have point sources, which is electric generating units. And then I'll just tell you that we process that information in a variety of different ways, and then we make those emissions ready for this model called CMAQ. CMAQ stands for Community Multi-Scale Air Quality Model. It's developed by EPA. Prior to becoming a professor at Rutgers, I worked for EPA in the Office of Research and Development as a CMAQ model developer. And this is the model that's also used by the Weather Service to make air quality predictions in the summer. So when you hear it's an ozone alert day, the Weather Service has run CMAQ in conjunction with the WRF model that Scott talked about. And so we predicted different air quality scenarios, and then we used a model called BenMap that can calculate societal health costs associated with different air quality scenarios. Okay, so first things first. One of the very first things that we did is we started looking in detail at the continuous emission monitoring data in the National Emissions Inventory. And I was teaching an undergraduate, Mike Moeller, who had a REI undergraduate research scholarship. And I was teaching him how to search files in Linux. And I made him grep for warnings and errors in our output logs. And what he found and what he discovered as an undergraduate here, first-gen college student, was that there was this quirk in the software. Continuous emission monitors at electric generating units get an identification number from the Environmental Protection Agency, and they get an identification number from the Energy Information Agency. And if they do not report both of those numbers, there's this quirk in the EPA processing software where it doesn't read in the continuous emission monitor data, and it makes up a temporal profile. Yeah, no one believed me, but it's absolutely true. And now, and it's in the literature now. So what was happening, and this was happening at almost, it was between 40 and 50% of the PJM facilities that have continuous emission monitors. So this blue line represents the actual output of PM 2.5 emissions from the continuous emission monitors. But this red is the temporal profile that was being assigned to that data. So if you calculate the annual average, you get the same exact annual average. But your model will probably overpredict in the wintertime and underpredict in the summertime. So I'm showing you examples. This was true for coal plants. This was true for gas plants. My group was really proud of themselves when they discovered this, and they like to make plots like this. SMOKE is the name of the EPA software, so SMOKE versus Carlton Group. And so I picked out an example from New Jersey. And so Caroline Farris now works at EPA, and she's correcting this problem. Okay. Okay, so that was first things first. And that became a side project that we didn't think we had to do. Okay, then the next thing that we had to do is when Frank's model predicts electricity generation, and we try to match that, sometimes it's very difficult. And so we decided to just go ahead and use Frank's model for comparisons when we tried different scenarios as our benchmark. So the way that we did that is we took annual emissions. I'm just showing an example for fine particles. And then we took annual heat inputs. And we developed unique tons per MMBTU custom emission factors for all of the electricity generating sectors emissions in PJM. And then we use those hourly emissions. And this was done by Mike Moeller. This was the undergraduate who made the discovery. And he now works at EPA Region 4. Okay, so Scott mentioned PJM. It's the largest energy reliability network in the United States. It provides energy for 13 states and 60 million people. And it's a market-based approach to predicting electricity generation. And I'm going to show you this example. Frank and I, maybe it took us 2 months to figure out this. Frank kept talking about emission permit costs, and I was so confused. I was like, no, you only buy your permit once. I don't know what you're talking about. But what Frank meant was you violate your permits, and that's a cost. And Gene Fox, we worked at Region 2, right? We call those fines, right? So he kept calling them permit costs. I was like, oh, you mean fine, right? And so that was one of the ways it took us to get calibrated to each other. Yes. Okay, so at the time when we did this research, there was 3 proposals, I think, pending before the BOEM, the Bureau of Ocean Energy Management. And so Scott Glenn's group, he talked a lot about the WRF modeling they've done. And so we used that same WRF modeling. This is from your group, Scott, surprise, and thank you. And so we used that meteorology that he used to simulate wind energy, and we used that the same way to drive transport in the air quality model. And this was used to show the results that I'm going to show you. Okay, so somebody asked this question before. We did an annual simulation with Frank's model, DASER, and we wanted to understand this 3,000 megawatt offshore wind project and how that would factor into PJM. So on the y-axis, I'm showing the percent of the total PJM dispatch attributed to that wind farm. And what I'm showing is not just New Jersey specific, this is PJM specific. The max is less than 3.5%. So there's lots of room. This is a really big facility, but it's actually a small fraction of total PJM. Okay, so I first want to show you the emission differences as a table, and I've been told that this table is boring, so please just hang in there with me for a moment. So what I'm showing, each row is a different category, so it's different pollutants, sulfur dioxide, which makes acid rain and particles, NOx, which makes ozone and particles, different particle sizes, organic gases, and then this is the energy difference. And this is the total for PJM, and then this is by each individual state in the PJM network. So most of the emission reductions actually happen in Pennsylvania, even though it's offshore of New Jersey. And I wanted to point out to Dean Farris that he moved to New Jersey just in time, because when we simulate installation of this wind farm, it changes congestion pricing for dispatch, and actually plants that weren't profitable under one scenario become profitable under another scenario, and emissions actually went up in Indiana overall. So just what I'm showing you here is just one example. It's just a few days. If it's a blue color, what that means is particle matter concentrations went down when we simulate installation of this offshore wind project. If it's red, that actually means particle matter concentrations went up. And so there are some episodic increases. And what I think this really, really highlights is the need for non-market pressures. So it's really important to have good governance and effective legislation that protects people and not necessarily relying on the market. So here what I'm showing you is just a summary of a summertime simulation averaging over time, because you can see it's pretty episodic. So while I was here at Rutgers, I testified to the Clean Air Council a couple times, and they would always ask me, well, what about the pollution that we're importing? And I would say, I will calculate that for you, but then we have to calculate how much we're exporting. And then they would not ask again. But I'm just going to show you, I did do those calculations. So here is the impacts on hourly maximum surface particle mass from all the other RTOs. The hotter the color, the higher the concentration. And then this is all of PJM. And as you can see, this is maximum total particle mass, and this is maximum total sulfate mass. So this is coming only from the electricity sector. And we're responsible, our electricity choices are responsible for most of the pollution that we experience. Down here at the bottom, I'm talking about peaking units. I'm not gonna have time to get into that into detail, but that was something that we spent a lot of time working on and talking about. Okay, and now this was the second part of that. So after we have these different air quality scenarios, we started to quantify health impacts. So on the left-hand side, I'm showing you the EPA model BEDMAP. And when Michael first showed me this figure, I really hated it. I thought it was ugly. And so Michael wrote his own software. And so we did that same calculation using finer scale data, using newer, more robust health calculation data. And so the thing that is really interesting is that even though the emission reductions were highest in Pennsylvania, the health impacts are actually greatest in New Jersey. Because when you normalize for population and you try to quantify the societal health costs, the benefit is largest here at home. Okay, so when Michael did this accounting for just the health, we used this very common formulation that's pretty standard in the literature. And the value of a statistical life, we used the EPA standard value of 5.5 million. And so the reduced mortality cost associated with this installation of the wind farm is this much money per year. And the cost associated with reduced morbidity, so less sick days, stuff like that, is this cost per year. And then when Scott was talking, there's another way, when you were talking about sea level rise, we tried to account for that. And so we also, in addition to the health costs associated with poor air quality, we accounted for the social cost of carbon. And so we focused on the CO2 emissions, and these are the assumptions that we use, $36 per ton, a 3% discount rate. And so we estimate from reduced carbon dioxide emissions, this is our annual valuation, and due to air quality health benefits, this is our annual evaluation. And so what I want you to take away is this is how much it costs every single year to not build a wind farm. This is absolutely a minimum cost, and it's definitely a lower bound. And Mark Rogers, he was a PhD engineering student who worked with us on some of these papers, and he's now a professor here. And he has a handful of papers related to this project. Some have very, very beautiful math. And the gestalt I take away from his work is that fossil-fueled electricity generation is probably not profitable without the human health subsidy. And so that's a choice that we make. We subsidize this electricity choice. Okay, so I wanted to tell you about agriculture impacts. So I'm very proudly a former professor at the School of Environmental and Biological Sciences. And when you're a professor there, you're instilled in this spirit of stewardship. And one of the ways that manifests itself is you write this thing called the Hatch Proposal. And this is a figure from my Hatch Proposal in 2015. So the x-axis is months of year, and then the y-axis is ozone concentration. And this is a pattern that kept repeating itself to me. So this black line is ozone concentration in 1998, and this orange line is ozone concentration in 2010. And I'm just showing these 2 years, and I'll explain why in a moment, but this pattern kept coming up. And so what we notice is that the maximum ozone concentrations are coming down, but ozone season is sort of expanding. We're getting higher concentrations early in the season. And why that's really important is blueberry plants are most susceptible to ozone damage when they're budding. And so now we're starting to see elevated ozone concentrations during budding season. And we are trying to relate that to blueberry production numbers, and that's why I'm showing these 2 years, because we are trying to normalize and account for storm damage the year before. Okay, so I was trained during my PhD in bench lab chemistry, and quality assurance was really, really drilled into me. And sometimes when you do modeling and you ask people about quality assurance, they start laughing at you. But I wanted to see if there was any evidence of electricity choice impacting air quality. So in 2003, there was a pretty large blackout. And the grid went down for some amount of time. And so that's kind of the opposite impact. We turned off a bunch of electricity generating facilities. Can we see an impact on air quality? And one thing I want to point out is that this blackout, my students picked this one because it has its own Wikipedia page, and they thought that was cool, is that this was caused by a stagnation heat wave event and an overburning grid, and that's increasing in intensity and frequency, and we need plots for Clint Andrews like that, right, for an NSF grant. Okay, so this is a map of New Jersey, the best state ever. And each orange dot represents a location that measured particle matter concentrations during the time in 2003 when this blackout happened. And if the dot is gray and orange, that means this sampling location was also operating during the blackout. So this x-axis is time, this y-axis is fine particle mass concentration, and then the box and whisker is the distribution across all of these gray sites. So this is the median, and then the distribution around the median. And so what we see is, things are cooking along, half of the power is lost, and particle matter concentrations drop dramatically. We turn the lights back on, and they jump right back up. And so if we make a choice about electricity, we will impact air quality, and we will impact air quality quickly. Now I'm also going to show sulfate, because most sulfate particle mass comes from power plants. They're not exactly co-located. So just to give some perspective on where they are. And so again, the x-axis is time. We see the sulfate mass concentration is up here. The lights go off, it drops dramatically, and then it jumps right back up. Okay, so if you take away anything from my talk, I hope it's that we should build this wind farm, and we should build more wind farms, and we should do solar power. And the thing that we're considering is actually just a small fraction of our total electricity usage. And our electricity is just part of our energy matrix. It's just one part of it. And so when we simulate this, most of the air quality benefits go to Pennsylvania, but most of the health benefits come to us in New Jersey. The other thing that I want you to take away is there might be these episodic changes due to markets that cause increases in pollution, and that's not something to focus on because overall the benefits are good. And I think that there is some uncertainty, and I think the best way to explore that uncertainty is in payback periods. So building the wind farm will eventually, not building it will eventually become more expensive than building it, and it's a when, not an if question. Okay, so I did none of this work by myself. I really am grateful to the Rutgers Energy Institute. Talking to people like Frank who come at these questions from a different perspective was really helpful. Like I said, Mike Moeller, we wrote 2 papers together with this scholarship, and that was really transformative. And the other thing I want to mention is Julia Daniels and Divya Srivastava were Aresti scholars that worked in my group. And Divya went to the College of Engineering, and now she's at Stanford. Thank you so much for your kind attention.
Plenty of time for questions. Jean?
Surprise.
No, please.
Where the benefits are, you're just talking really about the PJM states?
Yeah.
So I assume that New York and New York City would benefit immensely from health benefits as well?
That's absolutely right.
Make sure that Governor Cuomo knows that.
Yeah, I agree.
Yeah, let me write that down.
Yeah. Let me text him. I didn't think to text him that.
Yeah, you have his,
Yeah.
I have a dated one.
Hi, Annmarie.
Hi.
I'm Will Sullivan. I'm the former, now retired hairdresser from New Jersey. And I just wanted to add my agreement that the problems with the EPA modeling of ozone, particularly taking short-term emissions and turning them into long-term averages.
Right.
I know there's been a lot of work recently in trying to overcome that problem.
Yeah.
New Jersey and others, and there's been some success, but we still have the regulatory problem federal government for trying to regulate the daily ozone problem with a 5-month emissions trading system.
Yeah.
My question to you is, what do you think of the EPA 5-month emission trading system for solving our ozone problem? And how would you do it differently?
Okay.
Right, it's not a regulator.
Yeah. Okay, first I'm going to say, when I was here, I met Tonali Key, and I learned a lot from her. Okay, so I'm not an economist or a social scientist. I don't like trading. I can show you lots of examples where scrubbing solution gets really expensive, NOx trading price drops, and one power plant in Pennsylvania will emit more NOx than all the stationary sources in New Jersey. And so I'm a big fan of the Clean Air Act and the Clean Water Act, which were passed. EPA was created by a Republican president. And neither one of those acts assumes that we have the right to poison each other. And I think, I don't know, that's my thought on it. I don't know how to do it better exactly, but we're not limited by technology. Those are social problems, I think.
Other questions?
Thank you. As far as you're aware, have any of the generating companies started to look at these results and either modify their own operational procedures, both from a cost or an engineering perspective?
So both times when I testified to the Clean Air Council, there were people from that part, stakeholders from that group. And I did chat with them after. And I would say there was one guy who was really surprised. They pay a lot of money to maintain and calibrate those continuous emission monitors, and he was pretty angry that that data wasn't being used, and I don't blame him. So we've put those results in the literature. Every time I send my students out to give talks on this, they get jobs after. And so I think they're out there making a difference.
Great, one more and then we'll break.
Thank you. I know PJM is going through a whole process to consider issues just like this right now. And I was wondering if you've had any interaction with them, or if you know that some of the data that you referenced and that you've worked on has been part of that conversation at all?
No, not since I've moved to California. I haven't. I don't know, but we keep publishing on it. We just had a paper accepted last week. Almost accepted. Minor comments.
Great, thank you very much, Annmarie.